Right, okay, what is in fact the final lecture of Food Science and Chemistry on Patulin, continuing our short series on toxins in food. Okay, so we'll talk about what they are and what foods they affect. We'll look briefly at the regulations and then also talk briefly about detoxification methods. Okay, so patulin and pomes. What's a pome? You may well ask. You may well know. Pome fruits are members of the plant Rosaceae, subfamily Pomodiae. They are fruits that have a core of several small seeds surrounded by a tough membrane, so apples and pears, for example. The membrane is encased in an edible layer of flesh, so which distinguishes them from things like oranges, I guess. Now, patulin is a mycotoxin, that is a toxin arising from fungi, that primarily contaminates pome fruit products. But it's been reported from other fruit and foods, and also, for example, shellfish and cheese. Chemically, patulin is an alpha-beta unsaturated gamma-lactone, which we don't need to worry about too much. It's a secondary metabolite, and as I've mentioned, it's a mycotoxin. So if you remember, secondary metabolites are things plants produce outside their normal sort of energy and growth metabolism. These things are often associated with deterring predation. So patulin is a mycotoxin that can cause both acute and chronic effects in a wide range of prokaryotes and eukaryotes, including humans. So I've divided this into acute effects. That's to say, ones that happen sort of instantaneously, and then the more chronic ones, the long-term effects, reasonably good evidence of kidney damage, and there is some evidence it may be a possible carcinogen in humans. Certainly in some animal models there seems to be good evidence. So patulin's toxicity arises from its ability primarily to conjugate sulfhydryl groups, and there's a sulfhydryl group over there, which, as I'm sure you know, there are lots of them in food molecules, particularly in some amino acids in proteins, and also possibly by binding the bases of DNA. So a sulfhydryl group is a functional group consisting of sulfur bonded to a hydrogen atom, and plus, as usual, the R designating the rest of the molecule. And there's a picture of a typical contaminated apple, which has some structures on it, which we'll talk about in a second. So, Penicillium expansum is the main fungal species responsible for the contamination of pomes. It produces a blue mold, a soft fruit brown rot, which in time develops into blue conidophores and conida, which are larger scale fungal structures which have been drawn out there. Typical sort of hyphae type structures you see in fungi. There's a video on a link to a paper on the previous page, right, and have a read of that if you're interested. Okay, so regulations. EU has set limits on various things. Apple juice and cider is one of the main sort of products, but then the solid apple products, which would include the sliced apples you see in things like pre-packaged foods, and obviously a lower level in baby and infant food. There's lots of good methods for analysing these. I haven't covered them in these notes because they're not particularly relevant, but if you want to have a read the papers I've referenced. Detoxification methods we'll mention briefly. They are sort of potentially examinable. Again, Dow et al. Has a good review of the methods for detoxing patulin. It's a fairly recent paper. There may be more recent ones available as well, of course. So they divide the methods into physical, chemical and biological, and they also talk about disadvantages and safety, which I haven't covered here, but you might want to have a read of in your own time. As usual, there's a link through the paper there, and it's also a link from the notes page. This applies, I guess, generally to any sort of detoxification method, not just those for patulins. It should inactivate or destroy or remove the toxin, obviously, but it shouldn't produce or leave new toxic substances. Wherever possible, it should retain the nutritive value and the acceptability of the product. It shouldn't significantly alter the food processing technology of the product. If possible, it should destroy any fungal spores. And it should be practical as well and be economically feasible. So there are some general guidance for principles of detoxification. In terms of patulin, as I mentioned, these are the main methods, which are grouped into physical, chemical and biological. Again, read the paper I've just referenced if you're interested in more information. Clarification is an important stage in removing impurities from juice processing using adsorbents, and many juice processing enterprises apply it specifically to remove patulin in juices, but it's also how you get sparkling juices from, so the juices which don't contain bits, essentially. It's also used, that process is also used in the manufacture of beer as well. Looking down the chemical, the last physical methods, UV treatments have shown good effects in research models, but probably aren't effective enough yet for commercial operations, which is a pity because they are relatively cheap. Ozone's been shown to completely degrade patulin into carbon dioxide, oxalic acid, glycolic acid, and water at high ozone concentrations. But again, there may be issues with doing that on a commercial scale, handling ozone, for example. The biological methods refer to any methods which use active or inactive microorganisms or enzymes to reduce patulin in food. So obviously if they're using inactive microorganisms, they're probably relying on enzymes. Again, have a look at the notes. And that was the 100th video I've done this year, this semester, which is a lot.